Hello and welcome back. We are on lecture 5 in Fundamentals of Inorganic Classes. This lecture and the next two lectures all deal with chapter 3 in the textbook. So please be sure to follow along in the textbook. And what we're going to do in chapter 3 is to learn about different theories that govern what makes a good glass versus what makes a poor glass former. And this particular lecture here, the first part of chapter 3, is on structural theories of glass formation. So remember from the last chapter, from chapter 2, we introduced this volume temperature diagram. And what we saw from that is that if you have any liquid up here in the upper right-hand corner, if you are able to cool that liquid fast enough to avoid crystallization in this gray shaded region, what you will get is a supercooled liquid. It is this thermodynamically metastable state that upon continued cooling would give us the glassy state. And the glass here is a solid-like material with a liquid-like structure. And what we learned is that glasses could be made from any liquids provided that you cool them fast enough to avoid crystallization. But this didn't tell us anything about what types of chemistries of the liquid or what types of structures of the liquid would lead to good glass formation versus poor glass formation. All that we learned previously is that some liquids are easier to crystallize compared to others. But now what we need to do in chapter 3 is to dig deeper to understand what is it about the chemistry of certain liquids or the structure of certain liquids that leads to good glass formation versus bad glass formation. Or in other words, what liquids are very easy to suppress crystallization and therefore make good glasses versus liquids that are easy to crystallize and therefore are bad glass formers. And I'll also remind you of our definition of glass here. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale but continuously relaxes toward the liquid state. Note here, even in the definition, this doesn't tell us anything about the chemistry of glass. So what we want to do is consider what are some of the universal features of either glass chemistries or glass structures which lead to good glass formation versus not having good glass formation. This table, which is table 3-1 in the book, lists just a small sampling of different types of chemistries that can be formed into glasses by cooling from the molten state. There are certain elements here. So selenium, out of the entire periodic table, selenium is actually the best elemental glass former, although sulfur, tellurium, and phosphorus can also be cooled into the glassy state without crystallizing. Of course, many different oxides are very good glass formers, like boron oxide, silica, germania, and so on. Different sulfide compounds, so these are types of chalcogenide glasses, arsenic sulfide, antimony sulfide, selenides, tellurides, even some halide systems can form good glasses, some nitrate mixtures as well, sulfates, carbonates. There are many different types of organic glasses as well, even though we focus on inorganic glasses in this course. There are many researchers out there studying organic glasses, and this is just a sample of some of the many different types of simple organic compounds that can be cooled into the glassy state. Many polymers are also glasses. So most polymers that are non-crystalline are also glasses and have the same type of glass physics that the usual inorganic glasses have. And so certain types of polymer compositions are better glass formers than others as well. There are different types of aqueous solutions that can form glasses and metallic alloys as well. So some of these can form glasses by splat cooling. Others, such as bulk metallic glasses, can be cooled more slowly and still show good resistance to crystallization. And so there's another whole field of study, which is just bulk metallic glasses. So this is trying to understand which types of metallic alloys are better glass formers than others. So you can see there's such a wide range of chemistries that can all demonstrate good glass formation. What are some of the unifying characteristics here that lead these to form good glasses versus not? And here, just as another intro slide, the other thing I want to point out is that when we are comparing the crystal structure of a substance on the left versus a glassy structure, if we consider some compound here, for example, A2O3, where A is some cation, so it's some positively charged cation, and the anion is oxygen, that the basic structural unit is the same on the left-hand side as on the right-hand side. Or in other words, both the crystal on the left and the glass on the right have the same basic structural unit, where there's this A cation, which is the smaller black circle in the middle. This is the cation A, and the cation is surrounded, in this case, by 3 of the oxygen anions. Those oxygen anions are represented by the open circles. So there's a coordination of 3 of these oxygens around each one of the cations A. And then you'll note that each one of these oxygens is bonded to 2 cations. So every oxygen here is bonded to 2 of these cations A. And this is what gives us the basic structural unit of this crystal. And this basic structural unit of the crystal is identical to the basic structural unit in the glass. So you see over here on the right-hand side, in the glassy state, again, it is the cation here, A, that is surrounded by 3 of the oxygens, and each oxygen is surrounded by 2 of the cations. So this basic structural unit here, which is this triangular unit, is identical on both the right-hand side as on the left-hand side. And now the next question is, how do these units bond to each other? So if we take the basic triangular unit here, if you draw this triangle where the 3 oxygens surrounding the cation form the vertices of that triangle, in the crystal, all of these triangles are connected to each other in order to form these hexagonal structures. And so you've got 1, 2, 3, 4, 5, 6 of these triangular units that form together to make one hexagon. And every single one of these triangular units is a part of this hexagonal ring. And then the hexagonal rings are close packed to each other. So you can see that you've got a hexagonal ring here, another one here, another one here. And there is a high degree of order to the structure in the crystal, where you've got short range order, which is defined by this triangular unit. There's intermediate range order, which is defined by the hexagonal ring. And then there's also long range order, which is the close packing of these hexagonal rings. And in the perfect crystal, as shown on the left, what this means is that you've got short range order, intermediate range order, and long range order, so that if you know the positions of any of the atoms here, you know exactly where the positions of all the other atoms are, because it's all following a perfect crystalline lattice. Now, on the right-hand side, you can see that there is quite well-defined short-range order, that the basic structural unit here, this triangular unit, is the same on the right as it is on the left. The only slight difference is that there's maybe a bit more variation in the bond angle here between the oxygen, the cation A, and the next oxygen, where there's kind of a bit more flexibility in some of that bond angle on the right, and that contributes a bit to the disorder of the glassy structure compared to the crystal structure. However, if you go from the kind of well-defined short-range order to the intermediate range order, the intermediate range order is less well-defined. There's still some sort of ordering, meaning that these triangular units are bonded to each other and they are forming ring structures, but there's more randomness in the size of the rings. So you can see here, this is a relatively small ring where there's only 4 triangular units making this 4-membered ring. On the other hand, here, this ring here has 1, 2, 3, 4, 5, 6. So this is a 6-membered ring, which is very similar to the 6-membered rings over on the left, but it looks like it's got a bit more variation of the bond angles. Here, there's a larger ring. So this ring has 1, 2, 3, 4, 5, 6, 7, 8 cations in the ring. So this is an 8-membered ring. And as a result, from an intermediate range order perspective, there's a variation in the ring size, and this ring size distribution contributes to the disorder of the glassy state structure. So well-defined basic structural unit of the triangle, but different number of triangular units come together to form different sized rings, and being able to fit all these rings together is what then leads to the greater disorder at the intermediate range scale and then at the longer scale. So if you pick an atom at one side of the glass here, because of the disorder in terms of the distribution of the different ring sizes and how they fit together, it's not possible to predict the exact positions of the atoms at a long distance over the glassy structure because of that increased level of disorder. Now, if we consider like different theories of what makes a good glass network versus not making a good glass network, many different theories have been proposed over the past century or so. And what we're going to do over the next 3 lectures is study the 3 most important theories of glass formation. These are the 3 most important theories in that they have all had a profound impact on how we think about glass forming ability as glass scientists. They are also the most important in that they have found good experimental evidence that proves that these theories are reasonable. And they are offering complementary perspectives on our understanding of what makes a good glass. So today we are focusing on the first type of model, which is a structural model. And specifically, we're going to cover what's called Zachariasen's random network theory. This is probably the single most consequential theory of glass formation. So we're going to cover this first. Then next time, we're going to take a different approach called a topological modeling approach. And the theory that we're covering next time is Phillips's topological constraint theory. And then 2 lectures from now, we're going to study the kinetic theory of glass formation. And combined, these 3 lectures will make up the entirety of chapter 3. So starting today and over the next 2 lectures, we are in chapter 3, studying these 3 different types of theories for glass formation. All right, so if we go back to 1932, probably the single most influential paper in the entire field of glass science is this one shown here. It was published by W.H. Zachariasen, and it's called The Atomic Arrangement in Glass. He published this in the Journal of the American Chemical Society back in 1932. Zachariasen was only 26 years old when he published this paper. And this is the only paper that he published in the entire field of glass science. And so at this young age of 26, and he was coming from a background of crystallography, he became basically the father of modern glass science by publishing this paper that had the most profound impact on our thinking of glass structure. And he started his paper with the statement here: "It must be frankly admitted that we know practically nothing about the atomic arrangement in glasses." And that was true. Going back to 1932, people didn't know anything about the structure of glass. And he says here, glasses are described as supercooled liquids or as solids. This gets back to our volume temperature diagram and our understanding now that glasses have a structure that's inherited from supercooled liquids, but behave mechanically as solids. And this question about whether glasses are liquids or are they solids, this goes all the way back to the early 1930s. And so this was at the forefront of Zachariasen's mind back then. The former term, so supercooled liquids, is justifiable from the point of view of physical chemistry, the latter from the theory of elasticity. It seems rather futile, however, to try to decide which of the two descriptions is the proper one to use when we are ignorant about the characteristic properties of the atomic arrangement. So Zachariasen is very astutely pointing out that we really can't give true answers to these questions about whether glass is a liquid or a solid or something else without really understanding the atomic structure of glasses. So that is what he attempted to do. And on this slide, I'm going to walk you through Zachariasen's thought process. So put yourself in Zachariasen's mind back in the early 1930s as he was trying to figure out what the structure of glass is. And this was kind of his rationale here. So he started out with the observation that since the mechanical properties of glass are similar to those of the corresponding crystal, meaning if you take silica glass versus a silica crystal like quartz, their hardness is similar, their elastic moduli are similar. So and there are differences, but they're more or less the same order of magnitude there. So the mechanical properties of a glass are similar to the mechanical properties of the corresponding crystal, that the atomic forces in both must be similar. What this means is that the bonding between atoms would be more or less similar between the crystal and the glass. So if we consider silica, for example, the bond that is relevant is the bond between the silicon and the oxygen. And Zachariasen deduced that this bonding between the silicon and the oxygen must be basically the same in a crystal like quartz as it is in vitreous silica or silica glass. Now, Zachariasen was one of the pioneers of using X-ray diffraction to study crystallography. And when Zachariasen used X-ray diffraction to study glasses, what he saw was what we saw in our last lecture, which is this very diffuse so-called amorphous hump coming from XRD. So there's no discrete peaks that come when studying glass from X-ray diffraction. And what this means is that there is a lack of any type of long-range ordering in glass. And Zachariasen deduced then that the diffuseness of the X-ray diffraction spectra, meaning this very broad hump that was observed, indicates that glass has an infinitely large unit cell. What this means is that the entire piece of glass is its unit cell, so the structure does not get repeated over space, and that's why we don't see these sharp peaks from the X-ray spectra. Therefore, glass consists of a random network in 3 dimensions. It has to be in 3 dimensions because he has a 3-dimensional piece of glass, and because it has an infinitely large unit cell, that means that the glass network must lack repeat units, which means that it has to be a random network. A direct consequence of this randomness would result in glass having higher internal energy than the crystal. So let's stop there for a moment. Since the crystal has kind of an optimum packing of atoms together, that corresponds to a minimum in the internal energy of the structure because all the atoms are getting in optimal positions. If you move them away from these perfect lattice positions, there must be some energy penalty associated with that. And so Zachariasen is deducing that the internal energy of the glass must therefore be higher than that of the crystal. But, to continue on here, but this difference in internal energy must be small. Otherwise, there would be a sufficient driving force towards crystallization. In other words, glass must have a higher internal energy than the crystal, but it can't be so much higher that it becomes so unstable that basically that huge difference in energy between the glass and the crystal would give you a very large thermodynamic driving force, causing the glass to be highly unstable and immediately crystallize. Next, this small energy difference requires an open and flexible structure. So glass, because of its non-ideal packing, must have a more open structure to accommodate the disorder of the glassy structure. So this is kind of walking us through Zachariasen's logic. Based on this logic, Zachariasen proposed 4 rules for glass formation. These are known as Zachariasen's rules, and these are the most famous rules or guidelines that are used for determining what would be a good glass structure versus not a good glass structure. So Zachariasen proposed 4 rules of glass formation, and Zachariasen was specifically thinking in terms of oxide glasses. So he considered an oxide compound where there's a cation A, and then the anion is the oxygen. So in the realm of oxide glasses, this would have a general formula of A sub M, O sub N. And so the M and the N here just govern the stoichiometry between the cation and the oxygen. This could be SiO2, this could be Al2O3, it could be B2O3, whatever the oxide is. The first rule is an oxygen atom is linked to no more than 2 atoms of A. In other words, the oxygen atom here, the oxygen is the anion, it has a charge of -2, and it is linked to no more than 2 of the cations A in order to satisfy that charge balance. The next rule, the second rule, is that the oxygen coordination around the cation A is small, say 3 or 4. So combined, these first 2 rules here are defining the short range order, which is found in glasses. The first rule tells us how many A atoms are linked to each oxygen. So there's no more than 2 of the cations linked to each oxygen. So the oxygen can provide a bridge between those 2 different cations. The second rule here defines, okay, how many oxygens are around the cation. And what Zachariasen is saying is that it should be a small number, specifically 3 or 4. So we've got 3 or 4 oxygens around each cation, and then 2 cations around each oxygen. And together, these first 2 rules define the short-range order for the glassy state. Why is it 3 or 4? It's 3 or 4 because the glass network needs to be able to build a random network in 3 dimensions. If we're living in a 3-dimensional space and we need to be able to make a glass that occupies this 3-dimensional space, that means that the glass structure must form this 3-dimensional network, which means that we have to be able to have rigidity in the network across those 3 dimensions. And in order for that network to extend in 3 dimensions, we have to have an oxygen coordination of 3 or 4 here. Otherwise, if it's less than that, you could end up with just like flat sheets or long rods instead of networks that extend in 3 dimensions. Okay, so if these first 2 rules here define the short-range order, the next 2 rules, the third and the fourth rule, define how these basic structural units are bonded to each other. So rules 1 and 2 define the basic structural unit. That basic structural unit is referred to as a polyhedron. This might be a tetrahedron, for example, in the case of silica, SiO2. A tetrahedron would have the oxygen coordination number of 4. It could also involve triangles, which would have a coordination of 3. So the general word for that is a polyhedron, and the plural of that is polyhedra. So this third rule here is that the cation polyhedra share corners, not edges, not faces. So in other words, if we go back here, the basic structural unit here is a triangle, and the polyhedron, therefore, is a triangle. It is centered around the cation here, this dark cation A. And how are these polyhedra connected to each other? They are connected by sharing the corners of the polyhedron. So each triangle here shares a corner with a neighboring triangle. And how these corners are shared together, that is what builds the overall glass network. So that's rule 3, that the cation polyhedra share corners with each other, not edges, not faces. If they were to share edges or faces, this would lead to a greater propensity for crystallization because it leads to a more closely packed network. Zachariasen deduced that a glass network, because of its disorder and because of its somewhat higher internal energy, needs to have a somewhat more open structure compared to the crystal. And we can get that open structure if the polyhedra are sharing corners rather than sharing edges or faces. And the last rule is that at least 3 corners are shared. We need to share at least 3 corners in order to build our glass network in 3 dimensions to make sure that the glass can exist and have a rigid network in 3 dimensions. So putting these rules together, the first 2 rules define what is the basic structural unit in terms of how the oxygens are coordinated around the cations and how the cations are coordinated around the oxygens. Once we've defined the basic structural unit, they're connected to each other through corners, and at least 3 of those corners are shared in order to build the 3-dimensional network. So these are Zachariasen's 4 rules. Make sure that you know each of these rules. Now, what I want to do is show you a picture of these rules. And this picture comes from a famous paper by L. Cooper. I'm going to return to this a little bit later. And it's from a paper that was dedicated to Zachariasen called W.H. Zachariasen, The Melody Lingers On. And figure 2 from that paper shows a picture of Zachariasen from the 1930s working on something here. And this is superimposed with the glass structure that had been proposed by Zachariasen in his original 1932 paper. So this is the first time that someone had proposed this random network theory of glass structure, and Zachariasen went so far as to actually draw this figure where he predicted what the structure of a glass would look like. And I will return to this in a moment as well. But what I want to show you here on the right is figure 3 from this paper shows a pictorial representation of Zachariasen's 4 rules. Here, this is that the coordination number of the cations around the oxygen is less than or equal to 2. So here, if you look at this oxygen is being shared at these 2 corners of the polyhedron. And you'll see that the oxygen is coordinated to 1 of the cations here in the center of this polyhedron, and then a second cation here in the center of this other polyhedron. So the coordination number of the cations A around the oxygen is less than or equal to 2. Next is that the coordination number of the oxygens around the anion. Notice that the subscripts here are switched. This means the coordination of the oxygens around the anion, that this number is small, specifically 3 or 4. And here you can see the cation in the center of the polyhedron, and this is shared by 3, or this is coordinated with 3 oxygens. So we've got 3 oxygens around the cation, and this is what forms our basic structural unit here of the triangle. If you were to have 4 instead of 3, then there would be another oxygen here coming out of the plane, and this would be a tetrahedron instead of a triangle. Now, Zachariasen's 3rd rule is that these polyhedra share corners with each other. Note here, this is a corner sharing between the 2 corners of these 2 triangles. They do not share edges, and they do not share faces. So this representation shown here has these 2 triangles sharing edges with each other, and that is prohibited because that would create a structure which is too compact, and this would lead toward crystallization. So the number of linkages between the 2 neighboring polyhedra, so this polyhedra to polyhedra linkage is just 1. So this means that the corner is shared. So this means only 1 of these oxygens is shared between polyhedra. If you have 2 of them shared, that would be edge facing, and that is prohibited. If you have 3 of them shared, this is like 2 tetrahedra with faces on top of each other, that is also prohibited. And then Zachariasen's final rule, the 4th rule, is that at least 3 corners are shared. This is in order to build the network out into 3 dimensions. And for the triangles here, you can see, in this case, all 3 of these corners are shared. If you have a tetrahedron, then there are 4 corners of the tetrahedron, and at least 3 out of those 4 corners would need to be shared. So these are Zachariasen's rules from a graphical point of view. And let's consider how this works here for our most common glass form, the one that we're going to study the most in this course is silica, SiO2. The question now is, does silica follow Zachariasen's rules? And this is the basic building block of silica glass. This is the silicon tetrahedron. What we can see here is that this silicon cation in the center of the tetrahedron is surrounded by 4 oxygens. So this satisfies Zachariasen's second rule, that the coordination of the oxygen around the cation is either 3 or 4. In this case, it's 4. Each oxygen here is coordinated with 2 of the cations. So it's coordinated with 2 of the silicons. So this satisfies Zachariasen's first rule. These neighboring silica tetrahedra are connected to each other by sharing corners with each other. So this satisfies the third rule. And then at least 3 of the corners of the tetrahedra are shared. For pure silica, it would be all 4 of the corners of the tetrahedra are shared. So the last rule is also satisfied. So we see here that silica satisfies all of Zachariasen's rules. And going back to this figure, this is actually Zachariasen's image of the glass structure on the right versus the crystal structure on the left. And one of his key insights is that even when the basic building blocks are the same, it's really the connectivity of those building blocks, how you put them together, that governs whether the structure is going to be a crystal, as on the left, or a glass, as on the right. Now, Zachariasen's random network theory was used to classify oxides as either being network formers or network modifiers, where if we want to have a stable glass, network formers are the species that follow Zachariasen's rules. Network formers are the predominant species in the formula for the glass chemistry, since they provide the backbone of the glass network, and they provide the connectivity that's required to construct this large disordered network in 3 dimensions. So some of the common glass network formers in various oxide glasses include silica and germania. These form tetrahedral units. They both form wonderful glasses on their own. B2O3, which has triangular units, and we're going to see later, can also form tetrahedral units. B2O3 forms a great glass on its own, or it can be incorporated into, say, a silicate network to form a borosilicate glass. Alumina actually requires some other chemistries in order to satisfy Zachariasen's rules, but alumina will form tetrahedral structures and can be incorporated into, say, a silica network to form aluminosilicate glasses. So this becomes part of the glass backbone. So this is also a network former. Phosphate also forms tetrahedral units, and we're going to see in chapter 5 exactly how that works, but phosphates also satisfy Zachariasen's rules, as do vanidates, and we're going to come back to that in chapter 5. In each of these cases, each one of these network formers creates a locally rigid structural unit. So either a tetrahedron or a triangular unit where that unit itself is locally rigid, meaning that the atoms do not have degrees of freedom that can perturb the structure of the tetrahedral unit itself. And this rigid cation-centered polyhedron follows Zachariasen's rules, and then the connectivity provided by the bridging oxygen atoms at the vertices of the polyhedron is what enables these polyhedra to link together. And so if you have a glass that has multiple components, maybe you've got a boro-aluminosilicate glass that has boron units, alumina units, and silica units. Each one of these oxides has its own locally rigid structural unit. The silica tetrahedron, the B2O3 triangular unit, the alumina tetrahedra, and all of these units come together to form the boro-aluminosilicate glass by sharing corners with each other. So the tetrahedra and the triangular units will share corners with each other. Now, the other classification of oxides are what's called network modifiers. With glass network modifiers, these are the components that are added to the system that change the bonding characteristics of the glass structure, but do not form the backbone of the glass network itself. So for oxide glasses, the usual modifiers are either alkali oxides like lithium oxide, sodium oxide, or potassium oxide, or alkaline earth oxides like magnesium oxide, calcium, strontium, or barium oxide. These oxide units, so these alkali oxides or alkaline earth oxides, do not satisfy Zachariasen's rules, meaning that they would not be good chemistries to build a random network in 3 dimensions. Instead, these are components that are added to the glass network formers to make, for example, soda-lime silicate glass is a sodium oxide, calcium oxide, silicate glass. So the main constituent here is the silica, and then you'd add sodium oxide and calcium oxide, and the sodium oxide and the calcium oxide modify the bonding in the silicon network. So for soda-lime silicate, about 75% of the network is silica. And what happens is that the sodium and the calcium go in there and they change the connectivity of these silica tetrahedral units. What they do is they will convert the bridging oxygens. So bridging oxygens are the oxygens that connect two tetrahedra together. They actually break up some of those bonds so that the bridging oxygens are converted to non-bridging oxygens. So it's reducing the connectivity of the glass network. This is what helps to lower the melting temperature of soda-lime silicate glass versus pure silica. The sodium and the calcium come in, they disrupt some of the bonding between neighboring tetrahedral units. So instead of having 4 of the corners of the tetrahedra shared, maybe only 3 out of the 4 of the corners are shared. This means that there's fewer bonds. This means that we can melt it at lower temperatures. The viscosity is lower, so it flows more easily at lower temperatures. But you still have enough bonds there, and still you have at least 3 of the corners are shared, so you can build this 3-dimensional network. So most species can be classified as either glass network formers or glass modifiers. Sometimes some oxides could play either role, and these are known as network intermediates. So when it's not straightforward to classify a given species as either a network former or a network modifier, it is called a network intermediate. An example of that is iron oxide. And the reason for this is that iron can exist in multiple oxidation states. It can exist as iron 2 oxide, which is FeO. When it's like this, it behaves a lot like an alkaline earth oxide, like calcium oxide. And in this case, iron 2 oxide behaves like a network modifier. However, iron can also have an oxidation state of +3, and iron 3 oxide is Fe2O3, and that behaves more like a network former. So iron can switch between behaving like a network modifier or a network former, depending upon its oxidation state. And therefore, we refer to this as a network intermediate. So we've got network formers that form the backbone of the glass network, network modifiers that modify that connectivity of the network somehow, and then network intermediates, which could play either role in the glass structure. Now, I want to return to Al Cooper's paper here. Remember Al Cooper, he was one of our glass greats from a previous lecture. He's actually my advisor's advisor, so he is my academic grandfather. And he published this beautiful paper back in 1982 called W.H. Zachariasen, The Melody Lingers On. And this was Cooper's tribute to Zachariasen, where he kind of gave some history of Zachariasen's work and also expanded on it by discussing some of the mathematics behind Zachariasen's rules and trying to bring some mathematical rigor to what Zachariasen had proposed to understand, okay, why is it that these 4 rules that Zachariasen proposed are so successful in enabling you to construct this infinitely large disordered network in 3 dimensions, as long as these 4 rules from Zachariasen are formed. So Al Cooper actually not just published the paper, he gave a presentation on the same topic right before publishing the paper. And this was at the University Conference on Glass, the sixth one that was held right here at Penn State back in 1981. So Cooper presented this paper, W.H. Zachariasen, The Melody Lingers On. Um, and one of the members of the audience there was a professor from Penn State, Rustum Roy. He was one of the founders of the Materials Research Society, MRS, and he was actually a rather vocal critic of Zachariasen's theory. There was still a lot of debate going on about whether or not Zachariasen's theory was valid. And at the end of Cooper's talk, Rustum Roy very famously stood up and said, the melody lingers on, but it is off key. And for the next rather long period of time, there's this big debate that happened on the stage there between Al Cooper and Rustum Roy, debating whether or not Zachariasen's random network theory was actually valid. And this debate actually goes back many decades before then. The biggest criticism of Zachariasen's random network theory actually came out of the Soviet Union by some Russian scientists. And they had proposed what's called a microcrystalline view of glass structure. And the microcrystalline view said that the glass is not completely disordered, but it is composed of really tiny crystals that are in some sort of a disordered matrix. So there's kind of a disordered matrix phase, but within that disordered matrix phase, there are these really tiny crystals, and these crystals are too small to be able to observe from X-ray diffraction, and that's why XRD doesn't show any peaks. So what they argued, and this was led by two Russian scientists, Lebedev and Porey-Koshitz, at the leading Russian Glass Research Institute, which is located in St. Petersburg, which at that time was called Leningrad, I believe. They argued that Zachariasen was wrong, and that glass actually existed of little tiny crystals. So they propose that, for example, a silicate glass is an accumulation of submicrocrystalline formations, so it being nano-sized crystals of various silicates and silica, and they call these crystallites. These crystallites are definite chemical compounds or solid solutions. Their chemical nature is determined by the phase diagram for the system that constitutes the glass. These crystallites are separated by some sort of amorphous layer in which the degree of disorder increases with the distance from the microcrystalline region. And the crystallites are not mere fragments of crystals. In reality, they are considerably deformed structural formations with more or less pronounced features of a crystalline lattice. So this was a debate that went on for decades. And really, the only definitive conclusion to the debate came in this work that was done about a decade ago at this point, maybe just over a decade ago. This was work that was done at Cornell University by a PhD student, Pinchane Huang, who is now a professor of materials science at University of Illinois. And she did the first direct visualization of glass structure using transition electron microscopy, TEM. This was done on a two-dimensional sheet of silica glass. You can see the two-dimensional crystal of silica is on the left. The two-dimensional glassy state is on the right. You can see here, these are the six-membered rings that are forming. This is in the crystal state. There are six-membered rings of silica. And you can see how these rings come together to form this perfectly ordered structure in the crystal. In the glassy state, oh, by the way, the silica are tetrahedra, so this is actually bilayers of the crystal and the glass. There's actually two atomic layers. The two atomic layers are identical. The fourth bond is out of the plane here. And so you can imagine two identical layers on top of each other. That's what we're looking at here in both the crystal and in the glassy state. And so the coordination number of the silica, it appears to be 3 here because the fourth bond is coming out of the plane. And then each oxygen here is connected to two of the silica. So around each one of these rings, there are 6 of the tetrahedral units. Now on the right, the basic structural unit is the same. It's still the silica tetrahedron, but what you can see is that there's disorder in how big the rings are. This is a 6-membered ring, just like in the crystal. Here is a 5-membered ring. Here is a 1, 2, 3, 4, 5, 6, 7, 8-membered ring here. This is another 8-membered ring, a 5-membered ring. And so you've got the same short range order because of having the same basic silica tetrahedral unit, but the intermediate range order is changing because there's a distribution of ring sizes. And because of that, then there's a complete lack of long range order. So this diagram here is nearly identical to what Zachariasen had proposed in his paper from 1932. So this was direct evidence that, in fact, Zachariasen was correct. And he predicted this about 80 years before the direct observation from TEM. So that is absolutely remarkable. And that's why one of our glass greats for today is, in fact, W.H. Zachariasen. He lived from 1906 through 1979. He was a Norwegian-American physicist and one of the pioneers of X-ray crystallography. He was not only the father of modern glass science, he was one of the pioneers of using XRD in the field of crystal chemistry as well. He got his PhD in physics from the University of Oslo in Norway in 1928, and he spent most of his career here in the United States working at the physics department at the University of Chicago. His seminal 1932 paper on glass structure established him at only 26 years old as the father of theoretical glass science, and his work is probably the single most influential paper in the field of glass, and his stature has only risen in the century following its publication. But I also want to highlight on the other side of the debate, one of the Russian scientists was Ivangy Alexandrovich Porykoshyts. He lived around the same time, 1907 to 1999. He worked in the lab that was headed by Lebedev, and Lebedev was the one to come up with the microcrystalline view of glass structure. Porykoshyts was working closely with him on that microcrystalline view, challenging Zachariasen. But in the course of his own research, Porykoshyts started to doubt this microcrystalline theory. He was tending to believe that maybe Zachariasen was right. Now, at this time, this was back during the Soviet Union under the Stalinist regime, this communist regime, and everything at that point in time was like this big ideological debate between East and West, between the Soviet Union and its communist system of government and all of its scientific theories, and the West and its democratic system of government and all of its ideas. And so this bled over into all aspects of life, including science as well. And so by kind of doubting the microcrystalline theory of glass structure, Porykoshyts was doubting like the official communist view of glass structure. And as a result, he was imprisoned. So Stalin arrested him and he was sent off to Siberia. And he worked in a prison camp there from 1936 to 1939. He was accused of supporting counter-revolutionary Western ideology because of this work in glass science. He eventually was freed and he returned to St. Petersburg, to Leningrad, and he kind of gave up on pursuing that line of research because of all the trouble that it got him into. But what he did is he shifted his research towards studying phase separation in glass, which we're going to cover in chapter 4. And he was a key pioneer in that area and had a lot of outstanding contributions to science in the area of phase separation. So we're going to be coming back to that in chapter 4. But I think we should all feel grateful that we are able to study science and exchange ideas with each other, based on the merit of those ideas without, the fear of political imprisonment. So Anyway, I wanted to highlight him as well because he showed tremendous bravery in doing the research that he did. All right, that's it for today. Next time we cover topological theory of glass formation, so we will continue on to that part of chapter 3. If you have any questions, just let me know. All right, thanks everyone. See you next time.